welcome.
Thank you. Hey, good morning, everyone. Thank you for having me. My name is Jakub Horn. I'm technical marketing engineer at Cisco, and for last 7 years, I work on SRv6. So it's my pleasure to give you some introduction, some overview of SRv6 in following 60 minutes. This is how service provider network looks like today. There are different domains with different technologies. The access domain is traditionally layer 2. Core domain is traditionally MPLS with layer 3 VPN. And in a data center, we predominantly see the VXLAN technology over the routed network. In access, we still see, well, in modern network, we see layer 2 VPN over MPLS. In some cases, we still see some older proprietary technologies like the bridging, and even the spanning tree is still there sometimes. This is difficult. This is difficult for every service provider, because to build any service, he has to build basically 3 services in 3 independent domains. One service in an access domain, second service in a core domain, and third service in a data center domain, which basically results in a long provisioning time. The troubleshooting there is difficult because he needs 3 different teams to take care of different technologies. Those technologies are, well, significantly different. And on top of that, he needs to take care of those stitching points between the technologies, right? To make layer 2 technology or layer 2 VPN to layer 3 VPN, you need pseudo-wire headend. And that's, well, there are a lot of issues with the scalability. There are a lot of issues with the troubleshooting. The technology is very, very complex there. And same with the DCI. If you need to do VXLAN towards the MPLS, there is a DCI, so which translate everything, and it's difficult and it's very complex. With the segment routing, we are trying to simplify that. We believe it's the right thing to do. It's just one technology end to end. So all the way from the cell site router to the TOR in a data center in case of MPLS, right? Which makes service provisioning much easier. So you need basically only 2 touch points, which is the cell site router and a TOR in a data center, to build one single service end to end, and everything is done end to end. Troubleshooting is easy. Well, the operation is very easy, and automation on top of that. Obviously, automation is much easier. If you have simple technology, the automation on top of that technology is obviously much simpler. This is for MPLS, right? For MPLS, we said, okay, let's go all the way from the cell site router all the way to the TOR. But with SRv6, we foresee the technology goes even further. We see the technology will really start on a G-Node B and will be terminated on the host itself, right? This never happened with MPLS. MPLS is still, well, kind of contained into the network, so only routers speaks MPLS, nothing else. But the IPv6 or SRv6, even hosts can speak, right? The Linux can speak, and the G-Node B is basically a host as well. It's typically based on Linux with some radio specific DSPs. So we foresee future with SRv6 really going end to end. The network will be just something much simpler than it is today. So here, I would like to introduce, and really from technical perspective, so I'm trying to avoid any marketing. I'll try to explain what SRv6 is and how it works. And you will try to figure out on your own whether it's good for you or not, right? I'll just give you the technical overview of the technology itself. I'll start with the data plane. And you will understand the data plane end to end. So you will see how the data plane works in SRv6. What is it doing, why it is doing so. Then I will spend some time on the network programming, which is just giving the logic, giving the terminology to SRv6 functions, and you will see what is that. And then I will spend some time on two most important control planes for service provider, which is IGP and BGP, and that's it. And well, if you have any question, please feel free to ask anytime. Everything in SRv6 is fully standardized. So I'm going along some standards. Well, and in internet, standards means RFCs, right? So we will do the RFC, and the main part of the data plane for SRv6 is, well, I don't remember number, but it's SRH, segment routing header. So I will do it here. So anything in SRv6 is just IPv6, right? Every single packet in SRv6 network is just plain IPv6 packet. And if I'll a little bit oversimplify, it's nothing else. Only thing we are doing differently in SRv6, we are manipulating destination address of IPv6 packet. And that's all the things we are doing. And well, not just manipulating, I think the most important part of that is we are giving different meaning to that destination address. It's not IP address anymore, it's something else. But we will get to that a little bit later. So destination address in IPv6 packet, in IPv6 header, is actually the most important field, obviously, right? The others are, well, important as well, but way less important. So destination address is the most important one, and we are dealing with the destination address big way. Second thing, well, second most important field in IPv6 header is next header. Next header was renamed from IPv4. It used to be called protocol, right? So basically it's for delineation what is encapsulated inside IPv6 packet. So here on this example, we see 6 means there is a TCP header after IPv6 header. So it is just what is inside the next header. And besides TCP, UDP, OSPF, ICMP, whatever there is a possibility to encapsulate into IPv6. There is a possibility to encapsulate IPv4, right? And it's quite common. It's happening very often. So you can take IPv4 packet and you can encapsulate it into IPv6 packet. Then your network, well, today is MPLS or VXLAN, but it can be just IPv6, and you can encapsulate everything into IPv6. Same way, you can encapsulate layer 2 frame, right? There is a next header field 143, which is for layer 2 frames. So any layer 2 service, well, end-to-end, either point-to-point or multi-point, can be encapsulated into IPv6 header. And then IPv6 transports layer 2 frames. The reason why the protocol was renamed to next header is exactly this. The IPv6 introduced the concept of header chaining. So you can have the IPv6 header pointing to next header. In this example, this is authentication header, which authenticates a whole packet. And in that authentication header, you can have another field, which is next header, pointing to TCP, for example, or again, that layer 2 frame, or IPv4. Or there can be the IPv6, then authentication header, then ESP header for encryption, and then any payload. And that concept we are in segment routing, we are using what is called routing header. Routing header was introduced day one of IPv6. It's really like 20 years old thing called routing header. It's supposed to be processed along the path, not on every hop, but on hops which are meant to deal with that, and we will see that again. And that's really the thing which is day one of IPv6. Over the time, there were different types of the routing header introduced, starting with source routing, some Nimrod, some mobility, RPL, I don't even know what is it for. But what we have done in segment routing, we introduce new type of the routing header, which is type 4, and it's called segment routing header, SRh in short. That header has couple of fields. Well, obviously, because it's segment routing means we are routing along list of the SIDs. Those SIDs are part of that segment routing header. There can be bunch of SIDs inside that segment routing header, up to, well, in theory, up to 255. And those SIDs are put into that header in kind of reverse order. So very first SID is basically at the end, so further from IPv6 header, and very last SID is close to IPv6 header. So we put list of those SIDs into the SRh, and those SIDs, well, we call them SIDs. They look like IPv6 address. They are basically 128 bits long. They really look like IPv6 address. You cannot distinguish whether it's IPv6 address or SID, but structure, meaning, semantics of the SID is something different, and we will cover that later. Then there are a couple of additional fields we are using there, and the one of them is field which is called segments left. I personally don't like that name because it's kind of misleading. I would rather call it active segment, because that field, segments left, is actually a pointer to the SID from the SID list, which is active. And the fact means active is that SID is always copied into the destination address of outer IPv6 header, right? That's the active SID. That's why I would rather call it active SID. And in segment routing, we are using this big way. So segment routing, SRv6, introduced new routing header type, which is called segment routing header, SRh, and we are using that for forwarding. I said, and again, we will have a little bit more details on that. The SID, segment ID, has certain structure. It's not IP address. It looks like IP address, 100%. It's basically 128 bits. You will see 128 bits. So it's just it's just IPv6 address. We put it into the destination address field of outer IPv6 header. So certain functions I really like IPv6 address, but it is not IPv6 address, right? IPv6 address always have TCP stack behind. So if well, you do telnet to IPv6 address, there is a IP protocol stack which pass your packets through towards the application, telnet or HTTP or any other application. SID is not like that. SID has different meaning, different semantics, different logic, and on top of that, it has structure, and we will dig into that structure a little bit more. Right now, we will split that structure into two portions. One portion, well, certain number of most significant bits. In here, it's 64 on that picture, but it can be anything. We call that locator. And that part of the SID is exactly like IPv6 address. It has routing capability, and it is always in a routing table. This is where, this tells you where the SID is located. And if every one of us is the part of SRv6 network, every one of us would have advertised into the routing protocol the one single, well, at least one single locator, right? Well, here /64, but it can be anything, and we will see that later. Then there is a function. Function is what to do with the packet, and I'll put that aside. We will spend quite some time on that later. Right now, I need that notion of the locator, and the locator is the routing portion of any SID or any device, and it is advertised into the routing table. And this is kind of the simple network here. We're very simple. Well, there are plenty of devices in there, and there is a source, and source can be anything. I said, well, in our way, it's typically router, but sometimes it can be host, or it can be virtual machine, can be container, can be anything. Relay source, which has an intent to send packet through certain devices in the network and terminate the packet on the router 4. The reason why the source wants to send the packet through different devices can vary. Well, in a network, it can be some form of traffic engineering, right? So I want to send the packet through certain routers, certain midpoints in the network to make sure, well, they are not following the shortest path, to make sure they are following, for example, lowest latency path in a network. So I need to build the packet in a way it will go through those devices before it reaches the destination. It's just intent, and intent can be anything. Well, you noted I work for Cisco, right? For me, it is typically routers, so I have always routers there, but it doesn't have to be routers. It can be firewall. My intent before reaching the destination can be, I'll pass the firewall. So R1 is the firewall. R2 can be IPS. R3 can be some content enrichment on GA interface. Doesn't really matter. It's just the intent. That intent can be anything. Also, those devices, they don't need to be physical devices, right? Well, even routers are not just the physical devices nowadays. So it can be the virtual machines, it can be containers, it can be anything. Only thing you need to have there is IPv6 reachability. And there is nothing special to that, right? We said every device in that segment routing network is advertising what is called locator. And each of those devices have unique locator. In this case, 2001 DB8 and the 0 and the device ID /64 in our case. And right now the source, and again, source can be the router or virtual machine or container or an application, wants to send the packet through all those devices before it reaches the destination, which is R4. So he will build the packet this way. So he will put their list of the SIDs belonging to each router. And he will put that SID there in kind of reverse order. So very first SID is in the first place, second SID is the one before last, and so on and so forth. And the ultimate destination is on the top. And he will set the segment's left pointer to 3, because 3 is the currently active segment. He will take the current active segment and he will copy it into the destination address. So current segment ID is copied into the destination address of outer IPv6 header. So intent is programmed into the packet, and packet is done, built, and it's sent out based on the routing table. And I said that the source can be either router or the host or an application, doesn't really matter. Anyone has, well, any device in routed network has routing table. Well, if it's router, it might have even full internet routing table. If it's host, it might have just a default route. Doesn't really matter. Obviously, he knows the route to everyone in the network, and he knows the route to the first destination. So he will send it on the interface towards the destination. Destination is router 1 right now. And between, well, me as a source and the first destination, or router 1, there can be multiple IPv6 routers. Those routers, and really, they can be really legacy old routers which doesn't understand any SRv6. They don't need to understand SRv6, because only thing they are supposed to do is to do plain, simple IPv6 routing. So what they're going to do, they will just do the destination address lookup, and based on their routing table, they will send the packet along the shortest path towards the destination IP address, which for them is 2001 DB8 001, whatever is beyond. So this way, packet will go through all the legacy routers and will reach the first segment routing capable, or first end of the segment, which is router 1. And router 1 will do 3 simple steps. He will decrement segments left, so active segment pointer is decremented by 1. That's a step number 1. Then he will copy new active segment to the destination address. So he will change the destination IP address of the packet, and he will forward towards the destination, and towards the new destination. A new destination is 2001 DB8 02 whatever. And again, he will forward it according to routing table. This is router, so probably have some little bit more complex routing table than just default route, and he will send it there. And again, between router 1 and router 2, there might be anything IPv6 capable, any router which is able to do plain simple IPv6 routing. Packet will get to the router 2. Router 2 will repeat those 3 simple steps. Decrement segments left, copy new active segment to the destination address, forward towards the new destination. Packet will get to the router 3, and router 3 is supposed to do, again, 3 identical steps. Decrement segments left, copy new active segment to the destination, and right now, well, he can forward it accordingly, but he can be smart as well. Smart meaning he wants to make life of the endpoint a little bit easier, and he wants to save some bandwidth on the link between R3 and R4, or on the network between R3 and 4. And he will do what we call penultimate segment popping. He will remove for SRh, because right now the segments left is 0, so he knows there is no more active segments to be consumed for anyone beyond him, so he doesn't care. No one in the network will ever need the SRh, so he'll just remove the SRh and will send it there. There is an option to keep it there. Well, it's up to him, right? I said, well, it's nice to remove that SRh, and most devices by default behave that way. But there might be a reason to preserve that. Reason to preserve that SRh could be, for example, I gave an example, R1 is the firewall, right? And right now the R4 needs to know, well, will only accept the packets which went through the firewall. Otherwise, it will get discarded. So I need to pass that information. The packet went through the firewall to the R4. And in that case, R3 would preserve the SRh. It's configurable. It's just different behavior of the SID. That's it. This is original concept of SRh, or segment routing v6, but it has couple of things there. I already said the SID has a structure. I split that structure into two sections, 2 portions. The first portion, the most significant bits, and in our case it was /64, is always the locator. That part is always exactly like IPv6 header. The second portion is what we call function. It's what to do with the packet. In our previous example, size of the locator was 64, size of the function was 64 as well. But it can be anything. It can be 80, it can be 81, it can be 25, it can be 40, 48. So I'll keep it simple. I'll make it 48. Then I have a function. It's very unlikely that any device in the network would have 2 to the power 80 different functions, different functionalities. So it's not very common. So function is usually a little bit smaller, and there is what we call padding. Just zeros, nothing, just some zeros, because we don't need to use them. We can split the locator further, and we are splitting that into the block and the node ID. And that was, if you remember that previous example, every router in that segment routing network has the same block. Sure, please, question. Yes, always, always. I didn't say that. Thank you for the question. Always has to be at the end. It's kind of logical thing, and we will use that later for some efficiencies. Yeah, padding is always at the end, and this is always the order. The locator is always most significant bits. Then there is a function, and there is a whatever left there. Back to the node ID. On previous example, you've seen all the nodes in that my network, because I'm service provider, all the nodes in that network, they are running, they are from the same range, same network. Only node ID 1, 2, 3, 4 was different. So this is the delineation. This is the trick. Same way with a function. Function can be function itself plus an argument. Does it remind you anything? Isn't it a little bit like programming language? Like in any programming language, you have the function or procedure, or whatever you call it, and you're passing certain arguments to that function. That's very typical, very common. Example in a networking. Well, the function can be shaping and policing. I'm the router. Maybe not a router. I'm QoS device, providing to any one of you the two functions: shaping and policing. And if you send me the packet on my function number 1, which is the shaper, with the argument 10 gig, I will provide the shaping functionality to 10 gig for that particular stream of the packets. If you send the packets on the function 2, which is my policer, with 50 gigs, I'll provide the policing of those packets to 50 gigs. Simple as that. In common scenarios, we don't have many applications for using the argument, so argument is typically not there. There is one exception. It's ESI filtering in EVPN scenario, but I'll skip that for now. So most likely the padding is bigger, function is smaller, and function is just I would say just static function without any argument in most cases, not in all of them. So in the network, and the concept I've just described, there is one glitch. There is one, I would say, even almost an issue. There is some suboptimal thing, and we don't want to do the thing suboptimally. And this is here. If I'll build, me as a source, if I'll build the packet which has to go through the network, I will build it exactly like this, right? I have, I believe, five different functions in the network, 5 different SIDs, and I'll put those 5 different SIDs into the SRh, one after another. And that block, that beginning for every single SID is identical. You see that, right? Because it's my network, it's probably contained within my network. My IPv6 addressing in my network is pretty much, probably, most likely based on the RIPE assignment, and beginning of the every SID is basically identical. Then there is always that padding on the end, right? There is always those bits which are not necessary. I don't have any use for them, and so I'm not using them. But I'm putting that into the packet actually 6 times, right? 5 times in the SIDs and once into the outer IPv6 header. And it has basically 2 issues. The overhead of the packet is too big, right? In this example, it's 5 times 16 bytes plus 8 plus 40, which makes it 128 bytes. Well, this is a lot, right? To transport any IPv4 packet, 128 is too much. And this is difficult for current hardware, right? For the legacy hardware, it's difficult. Legacy hardware is optimized to do the functions on very small IP header, so outer header, and it's not meant or wasn't never built to build like big overhead or do the lookup on the big overhead. So 2 issues. And I'm putting into the packet a lot of redundant information, which is not necessary. And we decided to address that with what we call SRv6 Micro-SID, right? Up to now, every single SID was 128 bits. Micro-SID can be anything less than 128. Again, well, the size can be anything. In our case, just for readability is 16 bits, and having said that, all the implementations out on the market is exactly the 16 bits nowadays. That 16 bits, they can have exactly the same functionality as those 128 bits. They're just 16 bits. You just squeeze that. You have a little bit less possibilities. You don't really need 2 to the power 80, and 16 bits seems to be reasonable, and we can play the size. We can put more if we need. And we put those micro-SIDs into the what we called SRv6 container. And the container is exactly those 128 bits, right, to fit IPv6 address destination field of outer IPv6 header. And we will prepend always the list of the micro-SID with what we called SRv6 Micro-SID block. In this example, it's 32 bits, but again, it can be anything. It can be 64, it can be 11, whatever number you imagine. At the end, we have what we called end of container, all the zeros. It doesn't have to be put there by the head end or originating node because it will appear there anyway. And this way, basically, the functionality or the same functionality can be achieved by the encapsulating the original packet into the just IPv6 header and into the destination. Oh, sorry, that was too much. Into the destination address. Instead of one SID, we will put SRv6 micro-SID container with five SIDs. And this packet function-wise are totally identical. They will provide exactly the same function. Well, if you ask why, this is the how, right? This is basically the same network like before. I want to have source, originating node, head end, whatever you call it, to send the packet to the router 4, and he wants to make sure packet goes through router 1, router 2, router 3. That's one thing, and he wants to make sure it is still compatible for all legacy routers somewhere in between. So it can go over legacy IPv6 network. So he will build the packet exactly this way. Right now, he will put set of micro-SIDs into the SRv6 container. He will prepend that by 32 bits of the SRv6 micro-SID block, and that's it. Right now, he's putting everything in what I would call right order, or a kind of logical order. So first router is at the first place, second router is after, and so on and so forth. For certain devices, he will put just one micro-SID, like 1 times 16 bits. For some other devices, which, well, providing a little bit more complex functions, he's putting 2, which is router 3 and 4. So he built the packet. Right now, the overhead is much smaller, right? Instead of, well, I don't know, 128 bytes, it's 40 bytes. And 40 bytes is basically just minimum overhead I can ever have in SRv6 network, because every SRv6 packet is essentially IPv6 packet. So overhead 40 bytes is just the minimum I can ever have. And right now, he built the packet. And I didn't say that. Well, and again, here, every router is advertising its locator. And because we said right now the SRv6 micro-SID block is 32 bits and the node ID is 16 bits, the locator will be always /48. Again, just an example. Apparently, all the implementation, not just Cisco, all the other vendors, they are using exactly this structure and this format. So everyone will advertise /48 nowadays. And he will send the packet. He will send the packet, well, build packet this way, and he will send it out. Obviously, everyone is advertising locator. Everyone knows routing information, how to get to the locator of everyone else. So router R, which is legacy router, doesn't understand any SRv6, doesn't understand any SRv6 micro-SID. He will just forward packet based on a destination address. So he will do the lookup 2001, DB8, 1, whatever is beyond, he doesn't care. He will just send it towards the router 1. And router 1 will do just 2 simple steps. And we call them shift and forward. So he will shift whatever is beyond the SRv6 micro-SID block by 16 bits to the left. And that way he will get new destination IP address, which is 2001 DB82, right? And he will forward it, shift and forward. and it will forward it towards the router 2 because new destination address is 2001 db8:2, whatever is beyond. And again, goes through a couple of legacy devices, doesn't understand any SRv6 Micro-SID at all, just destination address lookup. We'll get to the router 2. Router 2 will do, again, shift and forward. Shift by 16 bits and forward towards the new destination address. Same way to the router 3. Router 3, shift and forward. And right now, router 3, because his function is a little bit bigger, it's basically 32 bits or 2 times 16 bits, he will forward, he will do the shift not by 16 bits, but by 32 bits. New destination, and send packet out. And right now, the packet is pretty much the same like before, right? Just the destination function on the router 4, right? So this way, we do the same thing without unnecessary overhead. So it's much more hardware friendly, and it provides less overhead for the packet while it's preserving all the beauty of SRv6, which is IPv6 routing, right? Just all the legacy routers, they can still do that. So, question is, well, right now I said, well, we are putting everything into the container, right? And the container is 128 bits. And what if, well, 128 bits, if my micro-SID is 16 bits, I can fit up to six micro-SIDs there, right? No more. What can I do if I need more than 6 micro-SIDs? If my traffic engineering is something more complex, what should I do? What can I do? Well, here in this example, I have 11 micro-SIDs. So what should I do? Any idea? I'll split it. I'll split it into the 2 containers. I will have container 1. Container 1, I will have first 6 micro-SIDs. Container 2, I will have remaining 5. And if I'm building the packet, I will put first container into the destination address, the second container into the SRh. And here is one more trick done. I'm setting the segments left field, the active segments, to 1, but I'm not putting that active segment 1 into the SRh. Because that active segment is already in destination address, I want to save some bandwidth here, right? I'm just omit those 16 bits, but I'm pretending this is there. And how it works, on the right-hand side, there is, again, simple network with 11 routers. And this is what source done, and it will send it out based on a destination address. And it will reach the router 1, and router 1 will do shift and forward. Router 2 will do shift and forward. Router 3 will do shift and forward. So, and you see how the destination address is changing, how the packet is reaching the different functions on different devices. And again, routers in my example, in reality, it can be any device of any nature. Router 4, shift and forward. Router 5, shift and forward. And right now, you notice that at the end of the container, there appear the value 0000, and we said that is kind of the special micro-SID value, which is end of the container. Right now, we reach the router 6, and router 6 sees his micro-SID, and behind that, he sees end of the container. And end of the container actually means the packet is either for myself, or there is another container somewhere in an SRh. So he will check, he will see, okay, there is an SRh, so what I'm supposed to do, there is SRh, I will do what I've done before, what I've done with a full SID. So he will decrement segments left, copy new active segment to the destination address, and forward. But we said we want to be optimal, we do what we call PSP, penultimate segment popping, because that last container is already in a destination address. I don't need SRh anymore, so I will just remove an SRh and forward the packet. And this way, I will do shift and forward, shift and forward, shift and forward on all the subsequent routers, and well, at the end, I will reach my final destination. Okay, I'll skip this slide for the time, but we will get there. One more thing, which is important and which is nice. I would rather say nice than, well, important and nice, which is good. It's field which is called flow label. that field was the only field which was newly introduced in IPv6 compared to IPv4. In IPv4, nothing like that exists, right? There is no field flow label. All the other fields are there, but flow label is not there. Flow label, again, definition since day one, 20 bits, and flow label is essentially a field which allows encoding entropy to the IPv6 packet. And we are using that. We are actually mandating all the vendors to do the entropy encoding into the flow label. In MPLS, encoding entropy was always disaster, always nightmare. You remember fat pseudovar label, you remember the entropy label, which is actually 2 labels. There was always the issue with the different implementations, different behavior from different vendors. That's crazy. In VXLAN, entropy is disaster as well, because well, basically, that's the reason why VXLAN is having all the UDP header, right? Another 8 bytes just to encode entropy to the different ports. Here, we are kind of inheriting the thing from IPv6, or using that simple IPv6 feature. So, every ingress device of SRv6 network is kind of mandated to encode the entropy of the encapsulated packet into the flow label, right? And this is here. So encoding entropy means doing 5-tuple hash. So source address, destination address of the inner packet, source port and destination port, and the protocol. And we compute hash, whatever hash you like, and you will put that hash into the flow label field of the outer packet. And then any device in the network, any P device, any router, if he's doing 5-tuple hash, he is mandated to do 5-tuple hash, including the flow label, right? And that way you get the entropy of encapsulated flows. Otherwise, that entropy would have been lost, and those 2 flows would go over the same path in the ECMP fashion, and that could potentially result in a disaster in a network, or increase the significantly cost of building the network. Network programming. I said there is something on top of that. There is something different, and we are basically in MPLS. There is only one single construct. It's called label. Over the time, it's label. It's 20 bits, encoded in 32 bits MPLS header. But it's just a label, right? Over the time, we gave those labels different names. Well, sometimes we use transport label, sometimes we use service label, sometimes we say per CE label allocation, sometimes it's called node SID, sometimes it's called adjacency SID. And it's the mess. Everyone is using different terms, different meaning, different things. So what we decided to do day one is basically to give the meaning of all the SIDs which are necessary for replacing MPLS network, or MPLS network how it works today. So there are different flavors, and usually they start with the end. End means end of the segment. And this is exactly what we've described, right? It's just the shortest path to the node. End of the segment means decrement segments left, copy new active segment to the destination address, and forward accordingly. And there are 2 ways. There are many behaviors, many different behaviors, and there is a bunch of behaviors with keyword next. It's all the politics at ITF, and ITF is basically calling SRv6 Micro-SID CSID next. I'm not going to go into the details. All the industry is using SRv6 Micro-SID or Micro-SID or IPv6 Micro-SID, but ITF decided for many political reasons to use CSID next. So those functions are end with the next, which is exactly here. And this is exactly same behavior like node SID in SR MPLS, right? It's 100% equivalent of the node SID of of SRMPLS. So the same behavior, we just call it end for end of the segment. Then we have end.x, and x means cross-connect, which is not, again, not the best name. Cross-connect means to the particular interface. So just whatever you received, you will send it to the interface. So I received on, well, I will assign end.x to each interface on my router, and whenever I will receive the packet there, I will do shift and forward. So we'll shift the forward, I will change the packet, but right now I will not send the packet towards based on a destination IP address. I will always send it on the interface 10.0.0.0, which is on the top, right? Always there. And if I receive the packet 2001 DB83E001, I will always send it there, no matter where my routing table is pointing right now. And it's 100% equivalent of the adjacency SID in MPLS. 100%. There is no difference. It's exactly the same behavior like the adjacency SID in MPLS. Then I have the bunch of the functions which is called end.dx. And right now, x is still the cross connect, so send to the particular interface, to the specific interface this value was assigned to. And d means decapsulate. So this SID has to be always at the end of the stack. It cannot be in the middle. If it's in the middle, we will discard it. And we will always do the decapsulation of the packet, right? Of the inner packet. An inner packet can be IPv4 packet, and in that case I will use end.dx4 function, or it can be IPv6 packet. In that case I will use end.dx6 function, or it can be layer 2 frame, and in that case I will use end.dx2 function. There is a same bunch of the functions which are with DT for 6 in this example. Again, okay, I didn't say that previously. On this one is 100% equivalent of the per prefix or per CE label allocation in MPLS, right? 100% the same thing, identical. You just do the forwarding based on the outer information. Here, DT, same thing, and T doesn't mean, well, actually means table lookup. So I will do the table lookup, specific table. So into the specific verb. So it's 100% what in MPLS is called the aggregate label or per verb label allocation. 100% equivalent. In the RFC, there is a bunch of the functions with a bunch of the kind of the names, most of them starting with the end, and this is really just to replace MPLS functionality in the current network. So something is for layer 2, so for EVPN signaling, different behaviors for V4, V6, and the different behaviors for the binding SIDs. Questions? Time check. And I said, well, the last but not, well, it's still for service providers, this is super important part, control plane, right? So far, we covered just the data plane, how the packet looks like, what to do with the packet if it's received on the certain functions. That was the first part. Second part was just giving the meaning of the behavior of each function. Right now, we will discuss the control plane. And service provider network, there are two important control planes, IGP and a BGP. We'll start with the IGP. Well, we will start with the generic overview. Certain functions are advertised in IGP. Certain functions are advertised in a BGP. That's kind of logical. IGP is for underlay networking. BGP is for services, for service networking. So D functions, they are typically making sense only in overlay. On the other hand, well, just end or end.x functions, they are making sense only in the underlay. All of the functions we are advertising in BGPLS. BGPLS is basically collecting all the information from the devices and send it to the controller. A controller, they can use that function any way he likes, right? That's important. And I said that already. The most important thing is the locator. Locator, it goes always to routing table. Well, typically advertised in IGP. Sometimes can be advertised in BGP in case of large data center network, for example. So IGP, there are two IGP service providers are using ISIS and OSPF. On this slide, like a year ago, I still had the statement OSPF will follow soon. Right now, all the vendors' implementation is ISIS only. Well, at least I don't know any vendor who is supporting OSPF. And I kind of believed it will change. Well, we will start supporting OSPF, but it's not changing, and maybe it will never change. Reason for that is very simple. If you're service provider running ISIS today, you will just extend ISIS with the new IPv6 address family, and you will start doing all the SRv6 functionality. Simple as that. If you're running OSPF, well, you're obviously running OSPF v2 because your MPLS network is IPv4 based, so you're running OSPF v2. OSPF v2 doesn't support any SRv6. So OSPF v2 supports only v4. So you need to start totally different protocol, which is called OSPF v3. Well, almost only common thing between OSPF v2 and v3 is just the name, because it's very, very different protocol. So you are really starting totally different protocol on there, and they have to run as a ships in the night. So anyone so far who ran OSPF said, okay, instead of running OSPF v3, I will rather run ISIS with v6 support, because all the other SRv6 implementations and the customers are doing that. So currently, it's ISIS only. ISIS uses LSP, link states packets, and well, there are a bunch of information. Well, just to build the topology, just to allow to build the topology. And here, what we are adding for SRv6 is the locator. Obviously, locator has to be advertised. Under locator, we are advertising end functions or UN functions. With the structure, always with the structure. Same for the every interface. We already said we are advertising end.x function, so those adjacency sets we are advertising, and again with the structure. And on top of that, we are advertising what we call SRv6 capabilities. So how many sets I can encapsulate, how many sets I can decapsulate, and so on and so forth. This is example. What we are doing. I'll just stop here. Well, you see, we are actually advertising locator twice. Why is that? Why we are advertising locator twice? Now, some people are not supposed to answer because they've seen this presentation already. There are two reasons. One is SRv6 locator, which is the second TLV, but that SRv6 locator TLV wouldn't be understood by legacy routers, right? So router is actually pretending the locator is also a network attached to him to attract the traffic from the legacy routers. Okay, that's for IGP. BGP, same thing. And if I say BGP, I don't mean underlay BGP. Most service providers, well, I would say even all service providers, they are using IGP for the underlay, BGP for the overlay for the services. So BGP for the services. We want to preserve everything as it was before. So this is IPv6 network, and I'm not saying SRv6. SRv6 capable are only those two routers, ingress PE and egress PE. And try to imagine each PE has multiple verbs, and to each verb, this PE will assign different functions and DT4 functions. So this is VPN v4 service, but the same for VPN v6, and you will see same is for layer 2. So for each verb, it will assign the different function. Then all the prefixes in that particular verb, they need to be advertised to the over SRv6 network, towards the ingress PE. And this is advertised over known address family. This is VPN v4 address family. That VPN v4 address family we are still using exactly the same way, right? Exactly the same way. Same address family, same route target, same route distinguisher, well, same sets of route targets. Only thing we are advertising on top is that SID TLV function, nothing else with the structure, right? So the egress PE will advertise the function together with the prefix. Ingress PE will put that prefix into that his verb based on the importing route targets and create the forwarding entry with encapsulation towards this function. And obviously locator is advertised in a routing protocol. And then when the data plane comes, based on the received destination, ingress PE will always encapsulate the packet to the specific function. Simple as that, right? No SRH, unless I need some complex traffic engineering scenario. I'll do simple IP in IP encapsulation. And, well, locator routing information is known across all the network, right? So based on first 48 bits, the packet will get forwarded to router 3. And right now, what is nice here, I'm not saying what is actually split in this network. This router 1 doesn't need to know locator per se. It can have the summary, because this is just IPv6 routing, right? It can have just /32 or /16 or even default. So you can have ABR, you can have whatever, you can have BGP in between. It's just IPv6 routing. Everything is simple IPv6 routing. Same thing with EVPN, with layer 2. We want to do layer 2 transport, either VPLS or static pseudovar signaled by LDP. Here, we are moving everything to EVPN. EVPN just provides the ESI advertisement with the function. Right now, the function is not going to be ENT-DT4 or ENT-DT6. It's rather going to be ENT-DX2, right? Because this is just layer 2. And I'm expecting encapsulation of layer 2 frames. And always that function is coming from the locator. And locator is entirely routable. Then, when I'm encapsulating, ingress PE based on the received frame just encapsulates with the outer IPv6 header and forwards towards the destination. And that's it. This way, we are building much simpler network, end-to-end, and those networks are just IPv6 network. There is no MPLS switching. There is no BGPLU. There is basically infinite scalability using that routing. So, to conclude, SRv6 is here, and it's fully standardized. Everything except that compression is 100% RFC, different RFC numbers, different RFC names. Only thing which is missing, which is not yet RFC, is that compression, so that Micro-SID compression, which is already workgroup draft, which means it's going to be RFC pretty soon, maybe in few months. It is widely used. 2 weeks ago, I was at ENTC in Berlin. We've been doing the interoperability between other vendors. And to be honest, there wasn't a single vendor I wouldn't be aware of who wouldn't support all I've described today, right? Everyone is basically supporting SRv6 Micro-SID. On top of that, there are many open source implementations, either on the application, but for me, essentially, what is important is the networking stacks, and the SRv6 in Linux is supported since kernel 4.10, which is 7 years old. It is being widely deployed. This is just for Cisco what we are having, which deployments. There are other vendors having other deployments. It's rather for your reference. There are very interesting use cases between many customers, and well, all The ones here, they're references which can be searchable over the internet. And well, just to conclude, for us, important thing in the networking or in the computer science, the simplicity always wins. Simple things are always the things which are at the end used. And this is what SRv6 is. So SRv6 is ultimate simplicity, back to the roots, back to the IPv6 routing, or routing in general, back on the longest prefix match, and we want to get rid of all those workarounds developed over the years. And that's it. Thank you very much. So
thank you.
My time is up, so if you have any questions, I'll be around, so feel free to ask any time afterwards.
Right. Thank you very much, Jakub.